Hello, thank you for joining this talk. My name is Rakibul Hassan and I'm going to present our paper Automatically Detecting Bystanders in Photos to Reduce Privacy Risk. This research was done in collaboration with David Kendall, Mario Fritz, and Abukapadia. Many photos captured in public places contain bystanders in addition to photo subjects. When shared on online platforms, these photos reveal the identity, location, and other privacy-sensitive information of the bystanders to potentially an unbounded number of people. Many of these photos are shared publicly, thus using facial recognition systems, people can be automatically identified and tracked that threatens the privacy and safety of people appearing in these photos, including the bystanders who did not participate in taking or sharing these photos and may not even know about their existence. To protect the privacy of bystanders, researchers have devised different solutions. For example, Bo et al. Designed a QR code as a privacy tag to encode a privacy policy. People who do not want to be in others' photos may wear this tag to broadcast their privacy preference. The authors also created a protocol that can be implemented in cloud servers so that when the tag is detected in an uploaded photo, the corresponding privacy policy can be applied, such as obfuscating faces. Hene et al. Proposed another cloud-based approach where registered users can mark locations as private. This server would notify them whenever new images are uploaded that were taken in one of those marked locations. Another set of prior works attempt to prevent taking photos containing bystanders or removing them before sharing. In such systems, bystanders broadcast their privacy policy using, for example, mobile applications. A corresponding app for the photographers checks if the bystander is in any recently taken photos using identifiable information such as facial features of the bystander. If detected, either the photo is deleted or the bystander is obfuscated. Our goal is to eliminate the burden placed on the bystanders where they need to be proactive to protect their privacy and use specialized applications, share sensitive information such as facial features and location. Towards this goal, we propose a machine learning based system that can distinguish between bystanders and subjects in an image. Once this is done, any privacy preserving mechanism such as removing or obfuscating the bystanders can be done automatically. This system can be deployed as a cloud service so that photo taking devices and any social media platform can use it whenever photos are captured or uploaded. There are two primary benefits to this approach. First, it facilitates establishing a privacy by default policy by attempting to protect the privacy of bystanders without requiring them to use any specialized application or to share sensitive data such as facial features and location. Secondly, in addition to new photos, this system can be applied to images that already exist in devices or cloud servers. In this work, we define a bystander as a person who is not a subject of the photo and thus not important for the meaning of the photo. For example, the person was captured in a photo only because they were in the field of view and was not intentionally captured by the photographer. The context dependence of this definition signals the challenging nature of conceptualizing and distinguishing bystanders from the subjects. For example, the people in this photo look very different from one another, and the overall photo context needs to be considered to classify them as a subject or bystander. Sometimes there is not much difference between the visual appearance of subjects and bystanders, further complicating the task of distinguishing them based only on visual data. So here we outline our approach to tackle this challenge. First, we seek to understand how humans classify subjects and bystanders, so we conducted a user study to collect data from people. From this data, we determined what reasoning or rationale people used while labeling a person as a subject or a bystander. Then we identified what high-level intuitive features of a person in a photo are relevant to human reasoning. Next, we removed features that contain redundant information and created a set of minimally correlated features. Then we built regression models to approximate those features using raw image data. And finally, we train a classifier using the predicted high-level feature values. I'll go into details of each step in later slides. So we started with a user study where participants were asked to label people in photos such as those shown here as subjects and bystanders. The images were taken from the Google Open Image dataset. For the labeling task, we asked, do you think the person in the green box is a subject or a bystander in this photo? Participants responded with a 5-point Likert scale. Then they explained why they classified someone as a subject or a bystander. We curated a set of high-level characteristics of a person that are presumably related to the classification task, such as whether people in the photo are aware of and comfortable being photographed, whether they are willing to be photographed and are intentionally posing, whether the photographer intentionally captured them, and whether they can be replaced with other random people without changing the meaning of the photo. We asked participants to rate people in images according to these features. Here is one example question asking about the awareness feature. How strongly do you disagree or agree with the following statement? The person inside the green rectangle was aware of being photographed. We started with photos of 5,000 people and each person was labeled by at least 3 people. Out of 5,000 photos, 920 of them were not of actual people and they were removed. 56% of the remaining people in photos are labeled as subject and 37% are labeled as bystander. The next step is to determine what rationale the study participants used to distinguish between a subject and a bystander. For example, when we asked, why did you label the person in the green box as a subject? The most frequent responses were, this photo is focused on this person and they are taking up a large amount of space. The photo is about what this person was doing. The person looks similar to, is doing the same activity as, or is interacting with other subjects in this photo. For bystander labels, the most frequent responses were, this photo is not focused on this person. They were captured by chance. The person looks similar to, is doing the same activity as, or is interacting with other bystanders in this photo. In the next step, we investigate whether there is any relation between the reasonings we just saw and the high-level features that we collected data about. As an example, let's pick the most frequent reason for labeling a person as a bystander. This photo is not focused on this person. How is this associated with different high-level features? This table shows Spearman's rho as the correlation measurement. All of the correlation coefficients are statistically significant, suggesting association between not being focused in a photo and the high-level features. We repeated this calculation for the other reasons provided by the study participants and obtained similar results. In summary, the statistically significant correlations between the reasonings and the features suggest that the high-level features may be good predictors to classify subjects and bystanders in photos. In the next step, we study how these features are related among themselves to remove redundant features. To do that, we performed exploratory factor analysis, including all the high-level features plus some other features directly obtainable from a photo, such as size of the person, distance from the photo center, and total number of people in the photo. We extracted two factors. In the plot, you can see how each feature correlates with these two factors. These three features, pose, comfort, and willingness, are correlated more with factor 1 than factor 2, and we refer the underlying concept represented by this factor as the visual appearance of a person. Similarly, these three features come from the second underlying factor that indicate how prominent a person is in the image. All features under the same group contain similar information, so we just pick one from each group, namely pose from group 1 and size from group 2. We keep replaceable as it is associated equally with both factors, and photographer's intention as it doesn't associate with any of these factors. So we now have the final set of features and we can use them to train a classifier. But the problem is, other than size, none of them can be obtained directly from an image. So there has to be some intermediate step to get these features from the raw image. This is what we do in this step. We infer these high-level features using raw image data. To do that, we utilize several existing deep learning models and pass the image through them to extract intermediate features. The extracted features are then used to train regression models that will be used to predict the high-level features. One of the existing models we used is OpenPose, from which we extracted body joints and link angles. Jointly, they suggest the orientation of the body. We used another deep learning model to detect faces. The faces are then extracted and fed into a second model, which provides probabilities of 8 emotions based on the facial expression. We also extracted features from ResNet 50 model, which was originally trained to recognize objects, including people. So this is the full process of predicting high-level features from raw image data. Separate regression model was built for each of these high-level features. Finally, we use these predicted high-level feature values to train a classifier. Combining everything, here is the full process of building the final classifier. The image is used to extract intermediate features using several existing deep learning models. These intermediate features are then passed through regression models to predict high-level features. Combined in size, these features are used to train the final classifier. This two-step classification procedure resulted in 85% of classification accuracy. We built several other models for comparison. For example, another model trained directly with features extracted from ResNet, OpenPose, and emotion detection models yielded 78% accuracy. We hypothesized that the high-level features contain information more pertinent to the classification of subject and bystander with less noise compared to the features from which they were derived. Thus, the two-step procedure resulted in higher accuracy. What makes someone a bystander is still a subjective notion, and so it is hard to easily declare labels as ground truth. We grouped the images based on how many of the human annotators agreed with the final class level. For 34% of the images, all annotators agreed on the final class level, but for another 34% of the images, only 67% of the annotators agreed on the final class level, indicating ambiguity about the levels. We trained and evaluated the model separately on these two subsets of data. The classifier had 93% of mean accuracy in the first case, with a corresponding area under the curve of 98%. For more ambiguous images, where only 67% people agreed on the class level, our model demonstrated 80% of classification accuracy and 89% of area under the curve. To evaluate the generalizability of the model, we applied it over an entirely new dataset of 600 images taken from the MS COCO dataset. On this dataset, overall, the classifier had over 84% of accuracy. It achieved more than 91% accuracy for photos with 100% agreement among the annotators and over 78% accuracy for photos where only 67% of annotators had agreement. These findings demonstrate good generalization capability of our model. These are some examples of correct classifications. People bounded by green and red rectangles are predicted as subjects and bystanders respectively. These are examples of wrong classification. Again, green and red rectangles indicate predictions of subject and bystander as before, but here the ground truths are opposite of these predictions. To conclude, we propose a machine learning based model to detect bystanders in photos so that they can be automatically removed or obfuscated to protect their privacy. But the distinction between subjects and bystanders is often blurry, context dependent, and sometimes subjective, as evident from the findings of our user study. Thus, detecting bystanders in images is a challenging problem. We approach this problem by identifying intuitive concepts underlying human reasonings and building a classifier based on only a few high-level features that map to those concepts. This resulted in higher classification accuracy. Additionally, the decisions made by our model are interpretable as they are based on high-level intuitive concepts. Our proposed solution eliminates the need for bystanders to be proactive to protect their privacy and exchanging sensitive information such as facial features and location. Our solution applies to all past, present, and future images. Thus, it has the potential to protect bystanders' privacy at scale. With that, I would like to thank you all for your attention and express my gratitude to the co-authors of this paper. Looking forward to hear your feedback on this research.